Hi, so I'm here to talk about multi-resolution Gaussian processes. So why do we need multi-resolution modeling? Oftentimes, data set at very fine resolution is very difficult to collect or very difficult to generate. And those data sources are usually very sparse and difficult to obtain. So the core scale resolution data is usually easily available especially in developing countries where data resources are not very easily obtained. Um, and so we are interested in using the coarse resolution data, which might be of lower quality and might provide inexact modeling estimates um, in, in conjunction with fine resolution data set, which might help in doing more efficient modeling at the finer resolution to obtain better prediction estimates. The main takeaway is that our experiments are from atmospheric modeling, where we are trying to learn data sets at multiple scales. So it's whether the data is at multiple spatial resolutions or data at different temporal resolutions as well. And we make use of the autoregressive scheme, which was first suggested by Kennedy and Hagen in 2000 for multi-level modeling. So the idea is the high level data can be learned as a functional approximation of the lower level data set, where the linear association between the two models is learned as the rho scaling factor, and epsilon is the bias in the higher level modeling. The methodology that we use is Gaussian processes, which is one of the more popular machine learning methods for modeling. So similar to a Gaussian distribution where the mean and covariance can be fixed or scalar values, in Gaussian processes, we have a function that can be drawn from a Gaussian distribution where the mean and covariance are functions instead of fixed or scalar values. And usually the shape of the mean and covariance functions are determined by some hyperparameters, and the similarity that is learned through the covariance term is also determined by the hyperparameters that we learn. So for regression, usually we learn the hyperparameters first, which helps us in approximating the mean and covariance of the prior Gaussian process, which helps us in turn learning the posterior Gaussian process, which gives us the prediction function. The idea behind multi-resolution modeling is that we might have data at multiple levels. So here, the level 1 dataset can be the core scale data, and the level n dataset can be the finer scale dataset. So the idea is to propagate information from any kind of modeling that we do at the lower level datasets to inform and obtain better estimates at the modeling that we do at the highest or the finest level dataset. This was first proposed by Perdickaris in 2016 and then again in their work in 2017. And that's what we use here. In our Lawrence 96 system modeling, that is our atmospheric modeling dataset, we have data at multiple spatial resolutions. So different physical processes have inherent structure to define the spatial granularity. So a physical process with lower variability requires a coarser grid scale, a coarser spatial grid scale, whereas a very highly variable physical process would require a very fine scale grid to define the or capture the variability. Similarly, we have information about all the physical processes at different temporal resolutions so that we can experiment and learn how these physical processes vary with the difference in with different time step intervals. Here are the results on 2 of the experiments that we performed. So we are trying to learn the physical process Y from physical process X. In the first experiment, we have the physical process Y being learned as a function of physical process X. And this kind of modeling is being informed by a similar model that is being learned at a coarser temporal resolution data set. And we can see that the observed values and the results that we obtain from the multi-resolution Gaussian processes are very similar, both on the spatial scale on the y-axis and also on the temporal scale, that is on the x-axis. Whereas the predictions that we do by only using the model that we have at the finest level, that is at 0.5 delta t temporal resolution dataset, if we learn using only that dataset, we are unable to learn the spatial heterogeneity in the dataset. Similarly, if we use a different temporal resolution as our finest scale and learn using the data that we have available at 0.5 delta t temporal resolution, we again see that the spatial heterogeneity is not captured, and we are also not able to learn the full range of values that we observe in the Y process that we can see from the first pane here. So in order to aptly capture the temporal and spatial heterogeneity in our physical processes, it's important that we learn these patterns from multi-resolution data.